In a power plant, the steam cycle is essential to the production of electricity. The boiler heats water to produce steam, and the turbine uses the steam to turn the generator, which produces electricity. The condenser turns the steam back into water, and the cycle begins again. In this part, we'll take a look at boilers. A boiler does two things. It burns fuel to produce heat, and it uses this heat to turn water into steam. From the outside, boilers look like big boxes. Some may be over 200 feet tall. This boiler is called a drum-type boiler because it has a component called a steam drum on top. The drum collects the steam made by the boiler. The walls of vertical metal tubes that line the inside of the boiler are connected to the steam drum. These tubes are frequently referred to as water walls because they're filled with water. The steam that's used to drive the turbine is produced in the water walls. The water walls surround an open area in the boiler that's called the furnace. This is where combustion occurs. That is, where the fuel is burned. The burners that supply the fuel to the furnace are usually located either in the corners or on the sides of the furnace. These burners are designed to burn coal. If your plant uses oil or natural gas, the burners will be somewhat different. Now that we've seen where combustion takes place, let's turn our attention to the requirements for combustion. A boiler needs a continuous flow of fuel and air in order to maintain the fire in the furnace. Let's look at a typical boiler and see how fuel and air are supplied. We'll start with the fuel, which in our example will be coal. A conveyor system carries the coal from the coal yard to the plant. At the plant, machines called pulverizers grind the coal into a fine powder. There are several kinds of pulverizers, so your plant may use a type that looks different from this one. Once the coal is in the form of a fine powder, it can be delivered to the boiler. Let's look at an illustration of a boiler and its support systems to see how this can be accomplished. In this example, the pulverizer is located here. Air is blown into the pulverizer to carry the powdered coal to the boiler. In this example, an exhauster is also included and helps draw the coal out of the pulverizer. The flow of air through the pulverizer carries the coal into the burners in the boiler. Additional air is blown into the furnace by forced draft fans. This ensures that the proper amount of air is in the furnace to support the combustion of fuel. Once the fuel is blown into the furnace, it is ignited. The heat in the furnace raises the temperature of the water in the water walls. A mixture of steam and hot water rises up into the steam drum. In the steam drum, the steam is separated from the water. The water recirculates back to the water walls through large pipes called downcomers. After the steam is further heated by heaters called superheaters, it flows from the boiler to the turbine. This is what a typical turbine looks like. A turbine converts the energy from the steam that flows through it to mechanical energy that turns a generator. The main steam line from the boiler enters the turbine here. The generator is connected directly to the turbine by a shaft. In this cutaway drawing of a turbine, you can see the blades located inside. Each set of rotating blades is commonly called a wheel. Stationary blades, sometimes called diaphragms or nozzles, help direct the steam from one set of rotating blades to the next. The stationary blades look similar to the rotating blades, but they are attached to the turbine casing and they don't move. As the steam passes through the turbine, the stationary blades direct the steam to the rotating blades, causing them to turn. The steam gives up thermal energy, or heat, and pressure. The rotating blades cause the turbine shaft to spin, and that turns the generator. After the steam from the boiler gives up much of its energy in the turbine, it flows into the condenser. A condenser is a large heat exchanger. It removes heat from the steam and converts the steam back to water. We'll use this illustration to explain how a condenser works. Inside, there are many small tubes with cold water running through them. As steam is exhausted from the turbine, it passes over the tubes, is cooled, and condenses into water. The water, which is called condensate, drips into the bottom of the condenser. The area at the bottom of the condenser is called the hot well. A system called the condensate feed water system completes the steam cycle by sending the water back to the boiler, where it becomes steam again. Because the water is used over and over, the steam cycle is called a closed system. The condensate feed water system is actually made up of two systems. The condensate system removes the condensate from the hot well. Then the feed water system feeds it back to the boiler. The water that is pumped into the boiler is called feed water. It replaces the water that leaves the boiler as steam. In addition to pumping water from the hot well back to the boiler, the condensate feed water system also heats the water. This increases the efficiency of the cycle. The water is heated by heat exchangers called feed water heaters. They use steam extracted from the turbine as their heat source. This steam is referred to as extraction steam. Another important system associated with the condenser is the circulating water system. This system supplies the water that flows through the condenser tubes. The condenser circulating water system can be either an open system or a closed system. In an open system, the water comes from a large body of water, such as a lake, a river, or an ocean. It passes through the condenser tubes, where it picks up heat from the steam. Then it's returned to the source. So the water flows through the condenser only one time. In a closed system, the same water is used over and over again. A cooling tower is used instead of a large body of water. The water that passes through the condenser tubes continues on to the cooling tower, where it is cooled by air that flows through the tower. The cooled water then passes back through the condenser tubes to repeat the cycle. Another system we need to discuss is the make-up water system. Its job is to replace water that's lost from the steam cycle. Valves, pumps, piping, joints, and other parts involved in the steam cycle can all leak. Since it's impossible to prevent all leakage, water must eventually be added to replace the water or steam that leaks out. When more water is needed, the make-up water system feeds it into the condensate system. Water that's used in the steam cycle must be purified to keep scale and foreign material from accumulating in the boiler. The make-up water system purifies the water, which is then stored in tanks until it's needed. In this topic, we looked at three important components involved in the power plant steam cycle: the boiler, the turbine, and the condenser. We also discussed some systems that support the steam cycle: the boiler fuel and air systems, the condensate feed water system, the condenser circulating water system, and the make-up water system. Take some time now to answer some practice questions about what was covered in this topic. From the outside, boilers look like big boxes. Some may be over 200 feet tall. This boiler is called a drum-type boiler because it has a component called a steam drum on top. The drum collects the steam made by the boiler. The walls of vertical metal tubes that line the inside of the boiler are connected to the steam drum. These tubes are frequently referred to as water walls because they're filled with water. The steam that's used to drive the turbine is produced in the water wall. In this cutaway drawing of a turbine, you can see the blades located inside. Each set of rotating blades is commonly called a wheel. Stationary blades, sometimes called diaphragms or nozzles, help direct the steam from one set of rotating blades to the next. The stationary blades look similar to the rotating blades, but they are attached to the turbine casing and they don't move. The condensate feed water system is actually made up of two systems. The condensate system removes the condensate from the hot well. Then the feed water system feeds it back to the boiler. The water that is pumped into the boiler is called feed water. It replaces the water that leaves the boiler as steam. Steam flows from the boiler to the turbine because of differences in pressure. Steam, like any other gas or liquid, moves from areas of high pressure to areas of low pressure. The steam pressure is at its highest as it exits the boiler. The high pressure in the boiler pushes the steam out through the main steam line, through the turbine, and into the condenser. As the steam gives up its energy in the turbine and is converted into water in the condenser, the pressure drops dramatically. When steam first enters the condenser, it fills the available space. But as the steam condenses, taking up less and less space, a vacuum or negative pressure is created in the condenser. This negative pressure tends to draw more steam through the turbine and into the condenser. Once the steam is condensed into water or condensate, it collects in the hot well. Now the condensate has to be moved from the low pressure area in the condenser back to the high pressure area in the boiler. This is done with a series of pumps in the condensate feed water system. One pump, called the condensate or hot well pump, removes water from the hot well. Next, the feed water pump pushes the water into the boiler. Some plants use a third pump, called a condensate booster pump, between these two. Each pump along the line adds pressure to the water. By the time the water leaves the feed water pump, its pressure is high enough to overcome the pressure in the boiler, and the water is forced into the boiler drum. There is a relationship between steam flow through the turbine and the demand for electric power on the power generation system. This relationship is helpful in understanding why steam flow has to be controlled. Basically, if more power must be generated to meet an increase in demand, steam flow must be increased to cause the turbine to work harder to turn the generator. On the other hand, if less power is required, steam flow must be decreased. Another reason that controls are necessary is that the amount of steam flow to the turbine and the amount of water pumped back to the boiler must be equal. If they aren't, then either the boiler or the turbine will be damaged. Let's see why. Let's say that the amount of steam going to the turbine and the condenser is greater than the amount of water pumped back to the boiler. As a result, the water level in the boiler drum drops. Boiler tubes are constantly exposed to intense heat in the furnace. In fact, the temperature is so high that it could melt the tubes. The reason the tubes don't melt is that the water and steam flowing through them keep the tubes cool. If feed water flow doesn't keep up with steam flow, water boils off faster than it's replaced. Eventually, there won't be enough water to keep the tubes from overheating and failing. In this case, the boiler drum water level would rise. In a short time, this excess water would be carried out of the boiler drum, along with the steam, to where it could damage components such as the boiler's superheaters. Damage from mismatched steam and water flows can be prevented by controlling the flow of steam entering the turbine and the flow of feed water to the boiler. The turbine steam control valves are located in the main steam line to the turbine. They are used to regulate the flow of steam into the turbine. In this illustration of a typical turbine, the steam control valves are located here. If more power is needed from the generator, the valves are opened wider. This causes more steam to flow through the turbine, more mechanical energy to be received by the generator, and more electric power to be produced. The reverse occurs when the steam control valves are closed down more. When the steam flow is varied, the feed water flow to the boiler must be varied equally. In this system, feed water flow to the boiler is controlled by a valve in the feed water line going to the boiler. The feed water control valves are opened and closed to match feed water flow with steam flow. In some plants, this control is accomplished by varying the speed of the feed water pump. Other plants use a combination of both methods. Regardless of which method is used, the important point to remember is that steam flow and feed water flow must be controlled so that they're balanced. A specific amount of heat is needed to produce a given amount of steam. The source of that heat is the fuel that's burned in the boiler furnace. Therefore, a specific amount of fuel is required to produce a given amount of steam. Boiler fuel systems are designed to control the amount of fuel supplied to the boiler. In this part, we're interested in the basic idea of how a fuel system works. To illustrate this, we'll look at an example of how the amount of coal going to the burners of a typical coal-fired boiler is controlled. Coal is ground into a fine powder in a machine called a pulverizer. Usually, several pulverizers are provided for each boiler. From the pulverizer, the powdered coal is blown into the boiler furnace and burned. Coal is fed into the pulverizer by a device called a coal feeder, which is located above the pulverizer. There are several different types of feeders. This is an illustration of one type of coal feeder. In this feeder, paddles move around, dumping coal into the pulverizer. Controlling the speed of the paddles controls the flow of coal. If more coal is needed, the speed of the paddles is increased. If less coal is needed, the paddles are slowed down. Boilers using oil or gas have regulating valves that vary the flow of fuel. When the amount of fuel increases or decreases, the airflow into the boiler must also increase or decrease to ensure proper combustion. This can be done by adjusting inlet vanes or discharge dampers on the fans that supply air to the boiler, or by adjusting the speed of the fans. The operation of a boiler involves balancing various flows, such as the flows of steam and water, and the flows of fuel and air. But at any time, the unexpected can happen, disrupting normal boiler operation. If such an event threatens the safety of people or equipment in the plant, you're faced with an emergency condition. Most plants have written step-by-step procedures for responding to emergency conditions. It's important that you know your plant's procedures and follow them. But since a procedure can't be written for every problem, you'll have to understand how your plant works in order to know what's happening and be able to take the right corrective action. Let's examine the general actions that should be taken during any plant operation emergency. Basically, there are three actions. First, determine the nature of the emergency condition. Second, put the plant in a safe condition. And third, return the plant to normal. We'll start by discussing how to determine the nature of the emergency condition. An operator's first indication that something is wrong is frequently an annunciator alarm. The alarm system monitors levels, temperatures, pressures, and flows in plant systems. If a variable exceeds a preset limit, an alarm sounds and an annunciator window lights in the control room. To find out what caused the alarm, the operator must check other indicators to determine the status of the system involved and any associated support systems. Then he can take the next step, putting the plant in a safe condition. If there is immediate danger, the operator must take immediate action to protect equipment and personnel. At this point, the emergency has been handled, but there's a third step. The plant must be returned to normal. Now that we've covered three general steps for dealing with a plant operation emergency, we'll apply them to a specific emergency. The loss of fire or flameout in a boiler is an emergency condition that requires immediate action. Frequently, operators can see the flame directly from the control room or on a television monitor. Some boilers have flame scanners, which are electronic devices that monitor the flame. If a flameout occurs and immediate action isn't taken, steam pressure drops. That's because the heat input to the water in the boiler has stopped, causing steam production to stop. After it has been determined that a boiler flameout has occurred, the next step is to put the plant in a safe condition. The real danger with the flameout is that a combustible mixture of fuel and air can collect in the boiler, because fuel and combustion air are still being fed into the furnace. If the operator simply relights the burners, the boiler could explode. In this case, to make the plant safe, you must first stop the flow of fuel into the boiler. Then you have to get rid of all the unburned fuel before relighting the burners. This is done by using the airflow through the furnace to blow the fuel out, an operation called purging. After the boiler has been purged, you must perform the third step, returning the plant to normal. In this example, that involves relighting the burners and increasing boiler steam pressure to normal. If for some reason the burners can't be relit, the unit must be shut down. Keep in mind that you must know your plant's emergency procedures in advance. If you wait until an emergency occurs to study them, it's too late. In this topic, we saw how steam and water flows through the steam cycle and how this flow is controlled. We also discussed the basics of how the flow of fuel to a boiler is controlled. And we discussed some basic steps for handling a plant operation emergency. This is a good time to check your understanding with some practice questions. Steam flows from the boiler to the turbine because of differences in pressure. Steam, like any other gas or liquid, moves from areas of high pressure to areas of low pressure. There is a relationship between steam flow through the turbine and the demand for electric power on the power generation system. This relationship is helpful in understanding why steam flow has to be controlled. Basically, if more power must be generated to meet an increase in demand, steam flow must be increased to cause the turbine to work harder to turn the generator. On the other hand, if less power is required, steam flow must be decreased. When the amount of fuel increases or decreases, the airflow into the boiler must also increase or decrease to ensure proper combustion. Let's examine the general actions that should be taken during any plant operation emergency. Basically, there are three actions. First, determine the nature of the emergency condition. Second, put the plant in a safe condition. And third, return the plant to normal.